Is it visible, sir?
Yes,
Full screen?
yes.
Okay. So am I audible, sir?
Yes,
Yeah.
yes. No problem.
Oh. So good morning to all. Thanks, Professor Vishwanathan, sir, for the nice introduction. So I will keep to your words. And before I start my presentation, I would like to thank the organizing committee and the technical committee of Indian Geotechnical Conference 2021 for choosing me as one of the resource person to give a talk on response of geosynthetic encased stone column supported embankments in soft clays. So I also take this opportunity to thank chair and co-chair of this session for giving me the opportunity to share our research ideas, which we have developed at IIT Kanpur and Tongji University. I had a collaboration with Tongji University. So I will be happy to share some of our result on this one. So my outline of my presentation will be a general introduction. And today also we have seen a lot of keynote lectures focusing on the challenges in soft clays and how to remediate it. And then we will see what is the need for encasing a stone column. And then briefly we will touch upon how the performance of the encased stone column is going to vary with the ordinary stone column under varied load conditions. And then we will see what is going to be the time dependent behavior of such encasement stone column. And if time permits, we will also look at centrifuge and numerical studies of geosynthetic encased stone column supported embankments. And finally, we will conclude by giving some new observations from our studies. So as we all know, the problems with soft clays, right? So everybody knows that soft clay has very low under shear strength. So because of that, there is going to be very low bearing capacity. And then it also has excessive settlement. And because the permeability of the soft clay is going to be too less, right? It takes longer time for the soil to dissipate the excess pore pressure. So which indirectly suggests that the settlement is going to be a time dependent. So there are several techniques which is available to mitigate the soft clays, and the primary one is the preloading. Then we can also look for sand drains with preloading. Then quite often we use prefabricated vertical drains, which is very much successful. But when we use pre-VD, then surcharge is also very important to be placed. And then some novel technique like vacuum consolidation techniques, and then most popularly stone column. So in this presentation, we will focus on stone column related aspects. So as the theme is on ground improvement technique, like I believe that most of us are aware of what stone column is and what is the load transfer mechanism and stuff. So a brief introduction: the stone column is a vertical substructural elements which can be placed in field either by replacement technique or by a displacement methods. So generally it takes the load from the superstructure or from the earth structures by transmitting it to the adjacent area and through the base of the columns, primarily through compression, shear, or by rotation. So the installation of stone column is now almost standardized, and there are several advantages of using the stone column, both considering the static based load condition as well as for dynamic load based conditions. And there are several researchers have already worked on stone columns, and fairly the load transfer mechanism and the failure mechanism is already well known. So to cut short our discussion, so there are several ways with which stone columns can fail. So when we analyze it, we will have to know, right, in which mode the stone column is going to fail. So when we are considering the stone column as a load bearing member, so which means that the load is directly placed on the columns, then most of the time it's going to fail by crushing failure or by shear failure, punching failure. But more prominently, it is going to fail by bulging, because this is not a rigid material, or it's not even a flexible. So these stone columns are going to be semi-flexible. So when we consider the embankments loading, so then the stone columns can move a bit, right, like a sliding type of movement, or it can bend, or it can rotate, and then it can also have a composite failure mechanism. So once if we have a composite type of failure mechanism, so then there is going to be a problem with the superstructure. So as we all know that stone column derive their strength from the surrounding soil. So if the strength of the soil is good enough, then it's always better to go for stone columns. But when the strength of the soil is less, let's say for example, if the undrained shear strength of the soil is less than 15 kilo kPa, then it may not provide a sufficient passive earth pressure condition. So then it will lead to excessive bulging, and finally it might lead to a failure. So now the question to be asked is how to reduce this bulging and whether the stone column is going to work for soft clay or not. So definitely it's going to be a good improvement technique, but when it is going to be very soft clay, so whether the stone column will be able to handle it or not. So that this has forced a lot of researchers to work on this field, and there are several alternative measures has been considered. So one such technique is by encasing the stone column with the help of geosynthetic material. So the geosynthetic material is going to provide some additional confinement, and because of this additional confinement, it is going to generate or it is going to develop some passive resistance, which gives rise to a higher stability to the system, and thereby it also reduces the bulging. So in a way, we can improve the performance of stone column by encasing it with geosynthetic material. And there are several studies which has been already reported in the field-based case studies, right? The implementation of encased stone column is being practiced in several countries. But when we recommend encased stone column in Indian situation, not many people try to use it or take it for granted, right? So now stone column is being established. So now we need to know, right? So how to convince the field engineers to implement encased stone column. So in order to make them aware that how this works, right? So the encased stone column supported embankments on soft clays. So what we can always do is that we can always consider let's say embankment for a road or a railway structure which need to be stabilized with stone column or an encased stone column, right? So we can always consider by taking the full domain as a numerical study. But this, since the stage of this, the embankment and the road is going to be too large, so it's practically not possible to consider the full stage embankments. So what we can always do is that we can always take a slice of it, and then we can analyze how this is going to perform under the embankment loading, and then we can design it further, right? So if we are really interested to know what is going to be the load carrying capacity or the performance of the interior most column, so then we can always use the unit cell concept. So the diameter of the unit cell can be worked out based on the layout of the stone column or the encased stone column and the area replacement ratio. So accordingly, we will be knowing what is going to be the radius of influence of our column materials. So this is the first aspect of it. Second one is when we apply a load on stone column, right? So where to apply the load? Because when you apply the load only on stone column, so then it becomes like a load carrying capacity of that column itself. But in most of the cases, the loads are going to be shared by soft clays also, which is nothing, which is surrounded by the stone column. So whether to consider it partly or to the complete one, right? That's the question, which primarily depends on field situation and conditions. And if you are going to place it throughout the unit cell, then we also need to know whether we are considering a rigid loading or a flexible loading. So whether we are considering a equal strain approach or we are considering a flexible approaches. And then we also need to know, are we considering the effect of the embankment construction sequence during this analysis? Okay, so that we can do it by axisymmetric unit cell as one of the option, or we can also consider a 3D unit cell option. So there are several people from India as well as from abroad. They have extensively worked on encased stone column, and most of the works are related to the load carrying capacity of the encased stone column. So what we try to do is we try to work on the time dependent behavior of encased stone column supported embankments. So in order to understand how the stone column is going to behave under rigid or the flexible load conditions, so we have taken different numerical work, which is published axisymmetric model, and the length of the stone is 10 meters, and the thickness of the soil is 10 meters. So it's be the fully encased stone column, and the diameter of the stone column is taken as 0.85 meters, and the spacing of the stone column is going to be 2.25 meters respectively. So based on the patterns, we can come out with a radius of the unit cell and then area replacement ratios. And for this study, we have considered a stiffness of 2,500 kilonewton per meter, and we have modeled it by using the linear elastic material. The properties of the various elements and the modeling technique, you can always refer to the Tan et al. 2008 or our paper to know more about the material properties. So because of the lack of time, so I will not be covering how we have modeled it. Rather, we will focus on what is going to be the significance from the results, right? So what we have done is, the first, to start with, we have applied the load intensity of 100 kPa instantaneously, and we try to see how this load is transferred into this unit cell, and because of that, what is going to be the variation in the effective stress which is developed in column as well as in the soft clay. So for that, we have considered a closed consolidation boundary condition, and since the stiffness of the column and the soft clays are different, we try to use the interface element, and then we have modeled it by considering a plate for the rigid one. For a flexible, we have removed this plate, and then we try to apply the load directly on it. To see some of the results, right, the most important thing is, as a field engineers, we will be interested to know, so whether by utilizing this, right, whether the time is going to be saved, because we need to achieve the ultimate settlement at the earliest, and then what is, there is any way that we can reduce the settlement also. So this is the pattern, the settlement of the soft clay when we apply the 100 kPa loading, and then when we introduce the stone column into the soft clay, we can clearly see there is going to be a reduction in the ultimate settlement. At the same time, the time for attaining a uniform settlement is also going to be reduced, right? By encasing it with a stone column, right, with the geosynthetic material, so further reduction in the settlement can be noticed. So this is for the rigid loading condition. So when we consider a flexible loading condition, so we can clearly see the pattern of the variation is going to be almost similar, but the settlements are further reduced, right, in by considering the flexible loading condition. And the flexible loading condition and the rigid loading condition depends on our field condition, right? It's not appropriate to compare it, but if we have compared it just to understand the mechanism. So when we consider flexible load conditions, then obviously we will be anticipating there is going to be some differential settlement between column and the soft clay, and that is going to be more prominent for encasement, because by encasing the stone column, we are increasing the stiffness of the material. So obviously we will be having some differential settlement. So when we use it in the field, so we have to be cautious how to reduce this the differential settlement. So when we consider it as a rigid loading, which means the equal strain approach, so definitely we may not have this differential settlement. Okay, but we can clearly see the settlement of the soft clay is going to be less when it's going to be more for the flexible one when compared to the rigid one. So when we try to work on the effective stresses, right? So this is what is going to be the effective stress which is mobilized in the soft clay because of this loading. So when we introduce the ordinary stone column into it, most of the load is taken by the column, which we can clearly see it from a higher vertical stress which is experienced by the column material. So the soft clay is having the lesser vertical stress when compared to the actual one without treatment. So when we encase it, so obviously what we expect that more load has to be taken by the column, and then we can reduce the vertical stress onto the soft clay. So when the vertical stress is lesser, then obviously the excess pore pressures are going to be less, and then dissipation takes lesser time, right? So when we use flexible load conditions, we can see the column load is, or the effective stress in the column is going to be much higher when compared to the rigid load conditions, even though the pattern is going to be same. So what we need to understand from this is that, so based on the field situation, we will have to be, we will have to choose whether we need to consider a rigid or a flexible load cases. So the load transfer between the column and the soft clay can be easily understood from the stress concentration ratio, which is the ratio of vertical effective stress on column to the surrounding soil at the same depth. So when we try to plot the effective stress concentration ratio with respect to time for an ordinary stone column, so we will see that as soon as we apply the load, there is an increase in the effective stress concentration ratio, and there is a gradual increase in the effective stress concentration ratio with respect to the consolidation time. But beyond that, we will see that there is a drastic reduction in the effective stress concentration ratio during the consolidation period. So this we can see it for both loading as well, for both load conditions, be it a rigid or a flexible one. So the reduction in the effective stress concentration ratio implies there is a higher load is being transferred to the soft clay, and hence it takes more time for the dissipation of the excess flow pressure. So when we encase it, so we will see that further enhancement in the stress concentration ratio can be seen. And the for a flexible one, we get a higher value when compared to the rigid one. So if we need to further enhance the performance, so we can change the material stiffness. So by increasing the stiffness of geosynthetic material, so what we can see is that the lateral deformations are going to be less, because there is going to be a lot of hoop stress which is going to be developed, and the geosynthetic material can sustain that hoop tension. So the next important question to be asked is, so since we are going to introduce geosynthetic into the stone column, is there is any way that we can reduce the length of the encased stone column? So what we try to do is that we try to vary the depth ratio from 1 to 0.6, and then we try to see the performance of the encased stone column. So when for a particular loading condition, I am showing it. So we can clearly see with the reduction in the length of the encased stone column, there is a higher pore pressures are going to be generated, and then since there is higher pore pressure, then it takes longer time to dissipate. So we are moving from fully encased ordinary or partially encased stone column towards the soft clay. So this is what is going to be the pattern we can see. So this can be easily reflected in the settlement also, right? So the settlements are going to be more for floating condition, floating encased stone column when compared to fully encased ordinary stone column as well as for a GAC. So the most important thing is when we, the most important thing is when we try to introduce to understand the effective stresses between the column and the soft clay, and below this, so we can clearly see there is a variation. The higher load is taken by the column, and then the lesser load is taken by the soft clay. So when we consider the stress points below this column, right, we can clearly see up to certain consolidation time, it doesn't take any load, but beyond that, the soil has to take the load, and hence the effective stress constant, the vertical stresses are going to be increased. So this clearly shows that the soft clay below the floating column tends to carry the additional load, which the column and the surrounding soil could not carry because of the limitations of the depth ratios. So this is an interesting study which gives us the efficiency of the encased stone column with respect to the ordinary stone column. So in terms of the ultimate settlement. So we worked out with the reduction factor. So the ultimate settlement by considering the encased stone column divided by the ultimate settlement considering the OAC. So what we try to do is we try to reduce the length of the encased stone column, and we try to see where it is going to match with the settlement of the OAC. So if in field we are going to use OAC for a particular settlement, then what we can do it with encased stone column. So that was the whole thing, and we try to vary the stiffnesses of the material, and then we try to plot with respect to the slenderness ratio of the column, and then the depth ratio. So as we can clearly see for different encasement stiffness, right, the performance of the encased stone column is going to be much superior than without encasement. The lower the value of reduction factor implies the greater efficiency. So this study gives us a clear idea that encasing the stone column will give us the better efficiency when compared to ordinary stone column. But when you are working with floating columns, there is always a problem with the dissipation of the excess pore pressure generated on the stone column. So now we will move to the
Rajesh,
second part of it.
sorry to
Yeah,
interrupt. You'll be able to wind up in another 2 minutes, right?
yeah, yes, I will do that. So what we try to do is we try to introduce the sequence of the embankment construction sequence, right? So what we have done is we try to uh, apply the load of individual in the embankment sequence, and then we try to allow it to dissipate for some time. So, and then we can also model it by using the two-dimensional unit cell, 3D unit cell, 3D slice. So based on our results, what we could see is that the 2D unit cell is going to predict the higher values of encased stone column, and the reasonable prediction is going to be made in all modeling when we consider it for a soft clay. So when we really work on the 3D slices, we can clearly see that the column 1 is going to move this way, is sliding, and the column at the tip of the stone column is going to tilt. So in order to check whether this is going to happen in a real practice, so what we have done is we try to simulate this in the centrifuge modeling with 25 G as the gravity, and then we have taken a consideration of this soft clay, which has a shear strength of 25 kPa. So what we can clearly see is that there is a bulging of stone column, which is going to be seen when we don't encase it, and then the lateral movement can also be seen. Whereas with encased geosynthetic encased stone column, we can see there is the shift in there is a bending happens in the stone column. And when we try to compare the results, we will see that there is a increase in the effective vertical stresses and strains because of the stiffness increase. And as we have noticed from the numerical study, even in physical modeling, we could see that there is a drop in the stress concentration ratio. So we have simulated the same thing using a numerical tool, and because of some issues with the numerical study, we were not able to predict the excess pore pressures properly numerically. But what we have seen from experiments are perfect. And this gives us a comparison between the centrifuge model test and the numerical study. So we can clearly see how the failure modes are going to move when the stiffness is going to change, right? And then we also try to see what is going to be the stress concentration ratio, which is going to vary with respect to the depth. So which has not been attempted by many people, right? We try to use a single value of effective stress concentration ratio, but from the centrifuge and from the numerical study, we could see that the stress concentration ratio is going to vary with respect to the depth. So the new observations, so what we could understand from the brief study is that the effective stress concentration ratio of ordinary stone column increases up to a particular consolidation period, but beyond that, it drastically reduces. Whereas in case of encased stone column, no such reduction is seen. And then when we reduce the length of the stone column or the encased stone column, we will see that time taken to dissipate the excess pore pressure are going to be higher. And then the capacity is going to be lower. And when we try to compare the results with 3D slice with the unit cell models, we could see there is some disparity in the results. Primarily, what we need to do is we need to use the 3D slice if you are really interested in working on time-dependent characteristics of the embankment-based studies. So due to the embankment loading, what we have seen is the ordinary stone column experiences bulging in the top portion of the columns, right? So when it is away from the middle line of the slope, then it tries to laterally move. Whereas when we have this, when we are encasing it with geosynthetic material, what we could see is that, so in the center line of the embankment, we will see the compression, whereas when it is in the sloping period, we will see that it's going to bend towards the embankment. So since there is a difference in the stiffness between the encased stone column and the soft clay, so we can always use the basal reinforcement so that this limitation of differential settlement can be reduced. So there are some few references. If you want to know more about it, you can write to us. We can send our papers. And before I conclude, I would like to acknowledge my mentor, who is the chair of the session. So because of him, I learned about centrifuge modeling, and so how to do a research I learned from Professor Vishnuadam. And because of that, we could get some collaboration from Tongji University. So I would like to thank Professor Jeff and then Zhang. So with this collaboration, we got some good results. I was there in Tongji University for some time, and whatever results I have showed is all from the hard work of our students from IIT and from Tongji University. Thank you so much for your patient listening. I'll be happy to take few questions. Sorry if I would have taken a little bit more than what is allowed.
Yeah, thank you, Dr. Rajesh, for excellent and lucid presentation. I think maybe I have to ask Dr. Sharif and how the questions are asked, actually, whether in chat box it will come. The session coordinator, can you just tell me?
So as far as I understand, it will come on chat.
As of now, the chat box has not come. But I wanted to ask one question, if the time permits. I think otherwise, I request all the delegates who actually have listened to the presentation can also write to Dr. Rajesh at IIT Kanpur, so that you'll be able to give more explanation. Dr. Rajesh, when you simulated centrifuge tests, you installed stone columns at normal gravity, correct? And what about the
Yes.
embankment? Have you installed it during flight or at normal gravity?
No, actually, we don't have that in-flight simulator. What we have done is that we try to we have used the slurry as the soft clay, and then we try to stabilize a self-compacted state we have made by spinning it for 3 hours. And then we got the shear strength. And after getting the shear strength of the soft clay, so we have driven the encased stone column. And then we have made our embankment on 1G itself. And then we accelerated it. Yes. So this is one of the limitations, definitely.
Yes. I think otherwise, I think the stress paths are different, isn't it?
Different, yes, definitely. Yes.
Yeah. So maybe I think that's what I just wanted to know.
Sure.
I think I asked Dr. Divya whether she wants to ask some questions.
No questions, Dr. Rajesh. Very nice and excellent presentation. Thanks for sharing your response.
Yeah. Then I think I also agree with Dr. Divya, the co-chair of the session, for your excellent presentation. Okay.
Thank you so much.
Keep doing well and keep doing good work.
Thank you, sir.